Okay, so I'm come back with chapter 5, 5.1, 5.2, in part 2. In here, we're going to talk, we're going to start with example number 4. Let A be the area of region that lies under the graph fx equal to e to the negative x between x equal to 0 and x equal to 2. So in here, we're gonna estimate the part A. We're gonna estimate area A by taking the sample point to the right end point and using 4 subinterval. Okay, so we use 4 subinterval from 0 to 2, right? So let me from 0 to 2, right? I did, in here the graph did split it become 4 each sub interval. See that? So each interval here is about like 1/2, right? You see that? 1/2, 1/2, and 1/2, right? And if you use the right endpoint, then you will have say for at here is 0.5. You will have the first rectangles here, right? The second one is 1, so here, right? And the next one is 1.5. So, and the last one is a 2. So here is a 4 rectangles using the right endpoint. Remember that's for the height of the first one you're going to use as f 0.5, right? The second one you're going to use as f of 1, and the next one is f of 1.5, and the last one is going to be f of 2 for the height. And the delta x in here will be equal to you can use 2 minus 0 over 4, which equal to 1/2, right? So let's go back a little bit here. You can see the delta x. Do I have the delta x formula? Oh, here, right? The delta x is b minus a over n, right? So you can apply that formula for this, and then now you have the area will be, okay, so the area will be delta x time with f of 0.5 plus delta x times f of 1 plus delta x times f of 1.5 and plus delta x times f of 2. Right? And now you can see the area will be equal to 1/2 multiplied by you can factor it, right? E to the negative 0.5 plus e to the 1 plus e to the 1.5 plus e to the 2, right? And now you can have you can use a calculator and have the answer. Actually, it can be 0.6664 as the answer. Okay, so I will circle this as a final answer. Okay. So let's move to part B and see what they want. Okay, so this part B want to estimate the area A by taking the sample point to the midpoint and using 4 subintervals. So again, it's still from 0 to 2, and delta x still is b minus a with 2 minus 0 over 4, right, which is 1/2. And then now for each midpoint, you have, say, the first one is, 0.5 plus 0 divided by 2 is 0.25. So it's 0.25, right? It's using this midpoint. So I'm gonna have the height of this interval going to be f of 0.25, and I have this first rectangle, and then the second I use 0.75, right? Adding them together and divide by 2, right? So here we go. I have m of 0.75. Okay. Next one I have this one going to be 1.25. Okay, and keep going. I have this one 1.75. Keep going. Oops. And this will be the last one. Okay. So I have A will be equal to 1/2 time with let's have the factor with f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Right, you see that? Should this be okay, so now I'm gonna substitute for f of 0.25 gonna be e to the 0 e to the negative 0.25. Oh, did I do that for the first one here? Yeah, I should have a negative, right? I forgot that. Negative 0.25, and then plus with e to the negative 0.75 plus with e point and negative 1.25 and plus with e negative 1.75. And then if you use a calculator, you will get 0.8557 as the answer. So circle the final answer. Okay. So please keep in mind that the true answer, later I will show you when we learn about integral, it's actually going to be equal to 0.8647, right? 0.8647. So as you see, so look like for now, the midpoint estimation, it look like it's better, right? See that it's closer than the right endpoint. Okay. So In worksheet number 4, we have exercise to try number 10. I will let you guys to do it in the class. And A and B, okay. And then we're going to move to example number 5 here. Okay. So in example number 5, how can we handle the situation when part of the function is below? So you can see here is there's a below, I guess it's this area. I got this A1, okay. And then another area, let's say it is right down here, it's A2. Okay, A2. All right. How can we we find the area of this of this situation, right? We actually going to use the total area when we will be equal to A2, pick A, and then minus A1. Because in here, A1 can be a negative number, okay? Because it's below the x-axis, okay? So let's talk about net area and definite integral. So definition is less fx, let me highlight here. Let fx be a function on a, b. And we say the net area of fx on a to b is equal to a plus minus a minus a positive minus a negative. Let's say that. And in here, remember that a positive going to be the area under the graph of fx of y equals fx that above the x-axis. Okay. And the a negative will be the area above the graph of y equal to fx, but it's below the x-axis. Okay. So let's have so we have midpoint. The Riemann sums approximate the net area. So remember that the Riemann sum will approximate the net area. Let's have example 6. We're gonna find exact net area of fx equal to negative x on the interval from -1 to 1. Okay, so -1 to 1, right? So I have here is the first area, so area 1. Or I can say area positive, right? And this one is the second area. And I call this area negative because it's below the x-axis and above the x, right? Okay, so now the area positive will be equal to 1. This is a triangle, right? Right triangle. So you have 1/2 time with 1. So and 1, right? Time with 1 and 1. Well, this is just 1, right? See that? And that's equal to 1/2. For the a negative, it's going to be also equal to 1/2. See that? 1/2 time 1, 1. Here is 1. Here is another 1. And that will be equal to 1/2. So then the net area will be equal to a plus a positive minus a negative will equal to 1/2 minus 1/2 and equal to 0. That should be the answer for this one. If we talk about the net area. Yeah. So I'm gonna let you guys try the exercise 11. Find the exact net area of Fx equal to x minus 1 on negative 1 to 4. Okay. So I will move down to the next definition of the definite integral. So in here we have fx be a continuous function on a to b. The definite integral of fx from a to b is defined to be so this is called like the integral of fx dx from a to b. So this one, integral of fx dx from a to b will be equal to net area of f on a b. Okay. So main part. Because of this definition, you can use geometry to find some of this integral. Okay. Example 7, find the exact value of 0 to integral of square root 9 minus x squared from 0 to 3. So from 0 to 3, right? So we have the area over here. See that? 0 to 3. Okay. And for this function, for the function of this curve, we're gonna have it is y equal to square root of 9 minus x squared. Okay, use other colors instead of the red one. Okay, so then we have if we square it, I'm gonna have y squared equal to 9 minus x squared. And we can have this, the function become x squared, not the function, the equation become x squared plus y squared equal to 9. And it is a equation of the circle. And the circle center at origin. Like you should remember the formula of a circle equation. Right? So center, circle center at origin with the radius is 3. You convert this, become the general form. You can see that it clearly as x minus 0 square plus y minus 0 square equals to 3 square. And that's going to tell you circle center at origin, and the radius is 3. Then, so then the area of circle is, right? We usually know the area of circle is like pi times r squared, which is pi times 3 squared. That's going to be equal to 9 pi, right? And for this area, we know that it is 1/4 of circle, right? So this is 1/4 of 1/4 area, 1/4 of circle, right? So A will be 1/4 times 9 times pi, which equal to 9/4 pi is the answer. So let's circle this. Okay. Okay, so let's move down. Now we're going to talk about the relation between Riemann sums and integrals. Okay. So theorem number 1. Let mx be a continuous function on the interval from a to b, right? And Rn, Mn, Ln be the right, left, and midpoint Riemann sum. Then the integral of fx dx from a to b will be the limit of Rn for n go to the infinity, right? Goes to infinity. And also equal to the limit of Mn when n goes to infinity. And also going to be the limit of Ln when n goes to infinity. So what does that mean? That means the Riemann sum approximate the definite integral as the number of rectangles get larger, right? As use highlight, as the number of rectangles get larger, this approximation get better. As I mentioned in the previous lecture, in previous video. So when you have more rectangles, you get the estimation even better, right? Closer to the true area. Okay, so now the properties of the definite integrals. Let me use other color. Okay. So I have the choose some 6 choose statement over here. So firstly, f of x dx, the integral from a to b of fx dx can be is equal to negative of the integral from a to b. Sorry, from b to a of fx. So in that way. And any integral of any fx that the interval from A to A, it's just itself, like 1 point, and it should be equal to 0. The integral from A to B of C dx over here will be equal to C times B minus A, where C is any constant. Okay. And next one, so we have integral from A to B of fx plus gx dx can be split, become the integral from A to B of fx dx plus and minus integral from A to B of gx dx. And then integral from A to B of C fx dx can be rewrite as C times with the integral of A to B of fx dx. And lastly, we have the integral of A to C fx dx plus with the integral from C to B fx dx can be rewrite as the integral of A to B of fx dx. There is a not true statement that you may mess up with, which is the integral from A to B of fx times g of x dx, which is not equal to the integral from A to B of fx dx multiplied with integral from A to B of gx dx. Okay, so the integral of the product is not the product of the integral. Remember that. Okay, so now let's use the property of the definite integral to evaluate the integral of 0, 1, 4 plus 5x squared dx. We knowing that the integral from 0 to 1 x squared dx equal to 1/3. Okay. So we know we have the integral from 0 to 1 of 4 plus 5x squared dx. Okay, I need to have the parentheses, and then it equal to, I can split it, becomes two addition of the addition of two integral. One is from 0 to 1 of 4 dx plus with 0 to 1 integral of 5x squared dx. Okay, and then I can rewrite it as the first one is a constant, integral of a constant, right? You see a constant over here, number 3, right? So it can be rewrite as constant multiplied by b minus a. So I can have 4 multiplied by b is 0. So either b is 0, b is top, right? B is top. So you have 1 minus 0, 1 minus 0, right? And then plus with the other integral with a constant multiplied by a function of x. So I can move out the constant to be in front of the integral. So I have 5 times with 0 and 1 of x squared dx. Okay, now okay, so I have maybe I have to write as number 4, apply number 4 here, and I'm gonna say apply number 3 and number 5. Right. number 5 to get to this step. What else? Then I have 4 times 1 minus 0, which is 4, right? So it's 4, and plus with the next one. Can I convert it? I have I have the given tell me that, you know, the integral from 0 to 1 x squared dx will be 1/3, right? So I can just adding with 5 times 1/3, and that's gonna give me 9 1/3. So 9 1/3. Yeah. So actually, you know what? Let me have 4. So I have 4 and 3, 12 1/3 plus with 5 1/3 equal to 17 1/3. So I'm going to write 17 1/3. Okay. So this should be a better one. All right. So now I am move to derivative review. Okay. So recall a few most important shortcut derivative rules that we have learned in derivative chapter. So we is derivative of xn equal to n times x power n minus 1, right? This is power rule. Some trigonometric derivative over here you may have to remove. So and the derivative of a natural log is here, right? Or log. And then the derivative of inverse sine, sine and inverse of tangent. Then a derivative of the exponential function. Okay, so and down here is Poirot rule, quotient rule, chain rule. Okay, so these are the things that we have learned in chapter 4, right? Now we will learn about antiderivative. Definition 1, right? A function f is called an antiderivative of f on an interval I if the capital F derivative x equal to Lx. So for all x in the interval I. So as you can see, antiderivative will you take derivative of the antiderivative, it will become the original function. See that? Right. Okay. So Let's do example number 9. Let's try to find some antiderivative function for fx equal to x squared. All right. So think about is there any function that when you take derivative you're going to get x squared, right? So I will think about something multiplied by x cubed, because later on when I take derivative of it, x cubed, I will get x squared, right? But then I still have to put the 3 in front of it when I take derivative. Then that means there's a 3 in front of it later when I take derivative. So in order to get rid of it, you need to multiply by 1/3, right? See that? You need to have 1/3, because later on when you take derivative of it, you will multiply by 1/3 and 3. They're gonna eliminate each other, and we have only x squared, right? So I'm gonna say because when you take the derivative of fx, we're gonna have 1/3 times 3 times x power 2. So that's give me x squared, which equal to Lx. Okay. Is there any other function that's when you take derivative of it, you will still get x squared? You will think about, again, you still have to take 1/3 x cubed, right? You will have always think about that, because the only way to get to that original mx equals to x squared is start with this guy. But then I don't want to make gx is the same as mx. So I'm gonna add with something. Maybe I'm gonna add with, I don't know, maybe 2, maybe that, right? Then when you take the derivative of it, system of 2 gonna be 0. So then you still gonna get fx, right? So because g derivative of x will be 1/3 of 3 x squared and plus 0, which equal to x squared, and which is again f of x. Okay, and then we come to hx. I wanna just summarize, or like have a general form in order to get to the fx after you take the derivative of that. So 1/3 x cubed, I can plus with a constant, right? So any constant, take the derivative of that will be 0. So I have a derivative of x will be equal to 1/3 of 3 x squared plus 0 will equal to x squared, and that's gonna be fx constant. So now you can say f, g, and h are all antiderivative. And I'm gonna say h of x is the most general. Okay. Okay, so now let's move down. A fact that if two functions have identical derivative on an interval I, then the two functions differ by a constant. So we have theorem 2, if f is an antiderivative of f on interval I, then the most general antiderivative of f on I is fx plus c for arbitrary or a constant c. So let's do an example to understand more of that. So example 10, find the most general antiderivative of each function, right? Okay. So for part A, if x equal to psi of x, you must have, so if capital of x or antiderivative of this one have to have the term as negative cosine of x, and you can add with a constant because to make it general, right? So because when you take away of that, you will get negative of a negative sine x, right? Because cosine x derivative going to be a negative sine x plus with 0, and that will be sine of x will equal to f of x. I see that. Okay, now for fx equal to x over n, with n not equal to -1, you can think about the f of x will have to have a x of n plus 1, right? And then I have to divide by n plus 1 in order to, when you take the view of n plus 1 later, this one later, you're gonna eliminate the n plus 1 term, factor, right? And then in order to make it general, I'm gonna process it with a constant. So say because when I take the view of that, I will get a n plus 1 times x for and then x for n and over n plus 1, and then plus with the 0. So because n not equal to -1, then I'm gonna just cancel the just gonna cancel the n plus 1, and now I'm gonna have x only would equal to x over n only would equal to f of x. Okay. Okay, now C. I have fx equal to 1 over x, right? And here, remember that there is a k with the ln x, right? So the antiderivative of s will be an ln of real x. Plus with a constant c. Because when you take away of that, right? Away of fx, you will get 1 over x plus 0 with equal to 1 over x and with equal to n over x. So remember that this only true on interval not containing 0. because if it becomes 0, then it doesn't undefined, it's undefined. Let's say x not equals 0. Okay. So for exercise to try number 12, let's see. Use a knowledge of derivative of basics function to complete the table antiderivative below for h and g. The task is to find the function f whose derivative is a given function f. So let's try to finish this, and then we can work together on in the class and see what happened. Okay, so let's move down, and we also have worksheet number 5. I will also let you guys do this. Okay, so I have finished session 5.1 and 5. From 4.9 to 5.2, 2, and we'll see you in session 5.3. Okay.